Hey guys, so today we're going to be talking about how the respiratory system works. And more specifically, we're going to be talking about ventilation, external respiration, transportation, and internal respiration. So we're going to start with ventilation. What is ventilation? It's the exchange of gas between the alveoli and the atmosphere. And this exchange is going to be allowed because of the differences in the partial pressures of the gases. So for example, in the alveoli themselves, there is a lower partial pressure than there is in the atmosphere. And that's why it's going to allow the oxygen to diffuse into the alveoli. Remember, things want to move from higher concentration to lower concentration. So that's more or less ventilation. So now we're going to move on to external respiration, which is this big thing I have drawn here. It's not that bad once we get into it. So we're going to start with the partial pressures in the alveoli. So we're going to have a partial pressure of oxygen of about 105 millimeters of mercury and a partial pressure of CO2 of about 40 millimeters of mercury. So what this is going to allow for is oxygen to diffuse into the red blood cell, because the partial pressure of oxygen in the red blood cell is 40 millimeters of mercury. So that's a pretty big difference. Now if we look at CO2, the partial pressure of CO2 in the red blood cell is 46 millimeters of mercury. What this means is that it's going to allow the CO2 to diffuse out, right, and come back into the alveoli, and then the alveoli can do gas exchange called ventilation, and then the CO2 is going to be allowed to exit, which is what we want. So let's look at it more in detail now. So in the alveoli, we have that oxygen coming in, right? And then the oxygen is going to diffuse into the plasma, and then after it diffuses into the plasma, then it's going to diffuse into the red blood cell. Once it's in the red blood cell, it's going to find hemoglobin. And when it finds that hemoglobin, it's going to kick off whatever it has on it. And when it kicks it off, it's going to become oxyhemoglobin, right? The HbO2 that I have written right here. And this specific one we're looking at, it was a hemoglobin that was bound to CO2. And that's actually how 20% of the CO2 is transported in your body. That's going to be important when we look at the other percentages in a little bit. So then, now that we have oxyhemoglobin, now we have free CO2. And remember, the difference in partial pressures is going to allow that CO2 to diffuse out into the alveoli, and then out of your body. Now, we're going to look at the other way we can get oxygen in. So the other way oxygen can come in is by kicking a hydrogen off of the hemoglobin. And then that's going to free up a hydrogen and create one oxyhemoglobin. So now that free hydrogen can join with bicarbonate, right here, and then along with carbonic anhydrase and form carbonic acid. Now that carbonic acid right here can join with another carbonic anhydrase and make H2O and CO2. Now this is how 70% of the CO2 is carried in your body, by bicarbonate in the plasma. So now that we have the CO2 can again diffuse out. Now what I didn't mention earlier is that when we have that bicarbonate diffusing into the red blood cell, we need to have what's called a chloride shift. We need to have this chloride ion shift out. And that's to keep an ion balance. Because this bicarbonate is negatively charged, we need to have another negatively charged ion shifting out. Yeah. And then the last way that CO2 is transported through the body is through the plasma. So we have about 10% of CO2 transported this way. Yeah. So now, we're going to move down to transportation. And what transportation is just the movement of CO2 and oxygen through the blood. So then, now you can imagine it traveling from the lungs, right, from the lung capillaries, this is where the external respiration was happening, traveling from the lung capillaries all the way to whatever other part of your body. For example, let's say my arm, right? It reaches my arm. Now what's happening? Now we need to exchange with the tissues that are located in my arm. So now we're going to do what's known as internal respiration. So the tissues in my arm, right, they're going to have a partial pressure of oxygen of about 40 millimeters of mercury, and a partial pressure of CO2 of about 46 millimeters of mercury. Now what this is going to allow for is it's going to allow the oxygen to diffuse into the tissues from the red blood cells right here, because the partial pressure of oxygen in the red blood cells is about 105 millimeters of mercury. So then it's going to want to diffuse into the tissues, whereas the CO2 is going to want to diffuse out of the tissues onto the red blood cell. So let's take a look at that in more detail. So we have the CO2 in the tissue, right, that we said wants to diffuse out to the red blood cell. So now we have the CO2 diffusing out, and then now it's going to kick this oxygen off of this hemoglobin. What? I thought oxygen had a higher affinity. Not here, because look at the difference in partial pressures, right? The oxygen wants to move off, and it wants to go into the tissues. So don't worry about the affinity right here. So now we have the hemoglobin with the CO2 and a freed up oxygen. This oxygen can now move into the tissues. Perfect. Now we can do, we can make a bunch of ATP through the electron transport chain, right? Another way that CO2 can travel, like we were talking about earlier, was 10% through the blood plasma. And then the other thing that the CO2 can do is join with water inside of the red blood cell, and of course carbonic anhydrase to make carbonic acid, and then that carbonic acid with another carbonic anhydrase can make a hydrogen ion plus the bicarbonate. Now the bicarbonate is going to shift over into the plasma, and when it does that, of course the chloride needs to shift with it, so they're going to go in opposite directions because of the chloride shift. And then now this freed up hydrogen can kick an oxygen off of a hemoglobin, and then we're going to have the hydrogen hemoglobin as well as now a freed up oxygen, which can now travel back to the tissues. So I hope this was helpful, guys.